We're going to take a look at how much people lie, which I think is perhaps an important question. We used to accept as axiomatic, and frankly, we've heard it quite a few times yesterday and today, that people tell one or two lies a day. And having stated that proposition, we'd move on to our big questions, things like who tells more lies and why, and how do you catch a liar? Why are some people better liars than others? We just didn't think that the prevalence of lying, how much lying, was all that important or even that interesting. Science seeks explanations. It wants to know, why do things happen? Well, in an expanding world with big data analytics, there's a notion that why is perhaps a luxury, that what might be good enough. And think about Amazon. Amazon, they don't care who buys 50 Shades of Grey. They care who buys it and what else they buy. But I'll tell you, I think the smart money is on the notion that knowing what is going on helps us to figure out the right why questions to ask. And so this isn't particularly a new idea. As the Solomon Asch quote suggests to us, before we inquire into origins and functional relations, it's necessary to know the things we are trying to explain. So I'm interested in the phenomena, what happens. Right. So let's begin with our what question. Most of us are social scientists, and we like to think about average behavior. Describe things as they occur. When Tim Levine and Frank Boster and I did our first large prevalence study, which was published in 2010, we asked the question about whether or not Bella DePaulo's 1 to 2 lies per day was accurate. We figured that the rate of lying might be important, and there might be some differences that we could find. Things like the reoccurring question of who lies more, men or women. We were surprised to find that a representative sample of nearly 1,000 people in the United States, U.S. adults, gave us nearly the same result as Bella DePaulo, 1 to 2 lies per day. We were more surprised when we looked at the graph of the data, which is what you see here, when we plotted out the distribution and we saw something very unusual. A lot of people tell very few lies, and a few people tell a lot of lies. And based on this outcome, we hypothesized that other studies might show the same result. And guess what? We weren't quite surprised when we saw the result of some of these other studies. What you're looking at here, one of DePaulo's studies in that first frame, and as you come down, a couple studies that were done by George and Rob, which replicated DePaulo with a different modality for recording data. The next column, our data with adults, and we did a companion study with students. We then did a study with teenagers, which was a highly focused and a group that lies a lot more. The Halavy study of students in the Netherlands was done for a variety of purposes, but one of the reasons that it was done was to validate the notion that you could ask people, how often do you lie? Self-report. These, in fact, are all self-report studies. We had a large database that we got from the UK and analyzed. We saw the same pattern. DeBay in the Netherlands looked at a cross-section of ages from age 6 to age 77. Guess what? They saw the same pattern. And Jeff and his colleagues, the Smith et al. Study, looked at lies per 30 text messages. And guess what? They saw the same pattern. In fact, when we put all these studies right on top of each other, it's the same pattern. So it's the actual averages that we saw differ from study to study. There are differences in the studies themselves. There are differences in the ways the questions are asked. But the pattern of response is what's interesting here. Some people tell very few or no lies at all, and other people tell a lot of lies. Now, because there are different modalities, because there are different metrics that were being used, can we make adjustments? And sure, we can. This is the Apollo data. The dark dots at the bottom are lies per week. So some people, they were keeping a diary, and some people would report that they told no lies, or one lie, or two lies, or three lies. And if you convert that to lies per day, which is the way we're asking the question in most of our studies, you see that the pattern starts to look a little bit more like the pattern that we observe in our lies per day studies. There are a variety of problems with trying to convert between the scales. When we ask people, how many times did you lie in the past 24 hours? If they didn't lie in the past 24 hours, there's 0 lies. But what happens if they lied the day before, or the day before that, or the day before that? So we go through some gymnastics to try and convert the data, but at the end of the day, what you see is that there is this pattern of people telling a few lies, most people telling a few lies, and a few people telling a lot of lies. There are other problems with making this comparison. Some of the samples are too small. Those small numbers, we can sort of see the pattern in the George and Rob data, but it's not very good. It's not very useful to us. But we also learned that sample size is important. When we start to look at large numbers of people, what we see is that the samples start to converge on the pattern very clearly. When we've got small studies, it's hard to see that. And maybe that's theoretically important. Okay. So we were interested in breaking this down. We wanted to categorize people because we figured, well, if we look at people at one end of the distribution versus people at the other end of the distribution, maybe we'll see some differences in their behavior, some differences in their characteristics. I'm going to tell you a little bit about what we learned about these distributions as we began to try and put them into these pockets. Now, we call the people who tell very few lies normatively honest. If you accept, and just go with me on this one, because I know there's a lot of debate about what is a lie, what is deception, what is honesty. But for our purposes, we're looking at the numbers, and we're trying to operationalize the concept of honesty. And frankly, if a person is truly honest, if they tell no lies, if what they say agrees with the facts. And we think of honesty as occurring when truth-telling is more efficient than lying. And since that happens most of the time, we can think of that as the equilibrium state. Normative honesty, as distinguished from honesty, is the idea that most people are being honest, but occasionally they tell a lie. One lie, two lies. But that telling one or two lies doesn't really cause us to think of that person as a bad person, as a dishonest person, as somebody who lies a lot. It's just somebody who deviates from the norm every once in a while. So we wanted to describe these people, and we wanted to distinguish them. We wanted to figure out where in this distribution this notion of honesty ended and frequent lying began. And so we looked to a mathematical model of rare events, the Poisson distribution, and said if truth is equilibrium, then telling more than a couple lies must be a rare event, and the Poisson distribution is the way that we should describe these rare events. Now what you're seeing here is the dark areas. Poisson distribution, the interesting characteristic of a Poisson distribution is that the mean and the variance are equal. And if that mean is fairly low, you get the curve that you see over here in the dark blue or darker blue. But as the mean gets larger, and the variance stays the same, eventually you get to something that looks more or less like a normal distribution. Poisson works really well if you're dealing with small numbers. And so when we looked at the data, we said, well, there's too much data in the tail of the distribution for that to be, there are too many people telling too many lies for all of these people to be Poisson distributed. Maybe there are two different groups of people here. So if we start taking people out, if we start lopping off the tail of the distribution and recalculating the mean with what's left, eventually that mean and variance converge, and you get what we see here on the left, where taking other people out, what's left over gives you a data distribution which looks like the theoretical Poisson distribution. And if we keep doing that iteratively until the mean and the variance are equal, boom, we find a place to cut off, we chop off and say, okay, those people are normatively honest. And we have a residual left over. So we went through, we repeated the process with all of these different studies. So blue dots or purple dots show you the normatively honest. The red ones show the people we have been calling frequent liars. And you can see that if we apply the procedure, boom, we can divide the world between normatively honest people and those who are frequent liars. We called them prolific liars. We called them prolific liars in print and then decided, oops, you know, that was maybe a little harsh on all of those people because, you know, you've got this big spread of people on this long tail, and some of them really are prolific liars. Some of them do tell a lot of lies, but some of them are just sort of hung up there in the middle. So I said, well, let's just look at those people we're calling frequent liars and see if we can figure out which ones really are the prolific liars. And what we saw with that data, as soon as we took out the people we call normatively honest, what we were left with was a distribution that looked something like the one that's labeled Zipf. Setting aside the majority of the data, the normally honest folks were left with this very clear pattern. The residual from those studies with sufficient sample size fit a power function, a power law function. Power laws are pretty important in science. They're scale-free, which means it doesn't matter where you start, the pattern will be the same. They have this characteristic long tail, and they describe a lot of phenomena in nature. They describe things like the mass of stars distributed through the universe. They describe earthquakes. They describe events leading up to the extinction of species. They describe the human motor system. They describe the distribution of wealth. They describe the diffusion of innovations. They describe the use of words. Those of you who know Zipf's laws, much of it is written about the use of words. And as the sample of observations grows large, the criticality, that is the form of the distribution, becomes clearer and clearer. And so we are observing, and so what we're observing is that the frequency of lying follows the same pattern as a whole lot of other natural phenomena. I don't know about you guys. That strikes me as interesting. It raises the question, is lying a natural phenomenon? This notion of criticality and the power law function, the different ways that are represented, most of them are mathematical transformations, and one of the things that we tend to do is we tend to look at the log plot of the data of the number of lies and the frequency of people lying, and if you get a straight line, that's a pretty good indication that you've got a power law function and that it fits this theoretical distribution. We've been asked ourselves the hypothetical questions. What if? What if messages have weights? And we talk about white lies versus big lies. What if we factor in how many people hear our lies? I mean, it's one lie, the lie we tell, Or is it 100 lies if 100 people tell us those lies? Little playing around with numbers suggests that if we do those kinds of manipulations to the data, we still see these distributions. Well, okay, so again, we went back to our data. We looked to see how it fit. Here's the DeBay study. Here's the U.S. Serota Levine, excuse me, Tim, and Boster study. And as you can see from the R-squared, not bad in terms of fitting the data. The whole list of our studies there that have enough data are shown. We get a pretty good fit using this. And if we take it one step further, transformation from Zipf to Pareto, which are both power law distributions, would give us some different information. We can fit the data, derive the shape parameter, and the shape parameter is related to the split between P and Q, the proportion of people who are on that long tail and everybody who's left over. And so in the case of our US data, what we find is 32% of the people are out on the end of that distribution. 68% are what we decided to call common liars. The 32% tell about 62% of the lies, of the frequent lies. And these are just all the studies lined up next to each other. We can see the result of applying the two procedures. First, the Poisson breakpoint analysis, then the Pareto shape parameter. And that lets us divide up the distributions if we have enough data. There are a couple studies that are too small. And in the case of Levine et al., our teenager study, teenagers lie so much. They lie so much that they don't fit the data particularly well because their average lies. If you remember that Poisson chart that I showed you, the overlaid distributions, they're out there where a high amount of lying is actually close to normally distributed. They just tell that many lies. So I guess that's the exception that proves the rule. Okay, and if we summarize all of that lie activity, lots of things going on here. But just to give you one example, if you read the line for the Dutch student, what you see is that 6% of all of their liars tell 39% of all the lies, and on average, 14% of the lies. Now, give me just 3 slides that are real quick. Really, really quick, okay? So what can we do with this? What's the implication of it? Once we break people up into these groups, we can look at all kinds of interesting things, like who these people are. So from the Halvey data, you can see the scatter plot of the data and very clearly see that younger people tell more lies than older people. As they age, lying decreases, particularly prolific lying. Secondly, we can begin to look at the characteristic lies. So in our UK data, we had big lies and white lies, and so we calculated the mean lies for each of the 3 groups, for white lies and big lies. And what we discovered was the prolific liars tell about 40 times more big lies than the people who are normatively honest. People who are normatively honest tell about 1 big lie a week. Everything else is little white lies. Prolific liars, they're just lying, and it just goes on and on. Okay, one more slide. I'm going. And I'm not going to make you read all that slide. So my quick comment is this: when we realize that lying is not normally distributed, and that half of lies, or half of the people are not telling half of the lies, but rather there are only a very few people that are doing most of the lying, that suggests that we do things like deception experiments, and which are normally done with half lies and half truths. that we're really gaming the system. And that part of the problem we have with our accuracy scores from detection experiments is the fact that we don't have the stimuli distributed in the way in which it actually occurs in the population. Most of the messages people get are truths. Only a small proportion are lies. And if we have different accuracies for lie judgments and truth judgments, and we've skewed the data, we're understating the accuracy fairly dramatically. Maybe just look at the last line there. So if what we see is a 30% lie judgment and a 78% truth judgment, and then I will shut up, overall, accuracy is a whole lot better than we would have otherwise estimated. I'm sorry.